Welcome back to module 2 of this course, time dependent quantum chemistry. In this module we are continuing discussion of Bohmian mechanics, and in Bohmian mechanics we have assumed certain trial function for the wave function which will give me time dependent probability density, which is important to have to represent quantum dynamics. And when we have discussed when we have used that trial function in time dependent quantum time dependent Schrodinger equation, we have got one velocity information. What does it mean by this velocity? We will go over it soon, but before we do that we will look at the one pictorial representation of what we have understood so far. This is standard quantum mechanics, standard interpretation of quantum mechanics, and this is Bohmian mechanics. It is just a different form of viewing the same problem on a different footings. So, in standard interpretation of quantum mechanics, quantum dynamics is represented in following way. I have a density which is xt dependent, and this is space. At time t equals t1, I have certain density. Let us say I have this density, and this is the time axis. So, I will call it, and different time I can plot how the densities would look like. So, what we are seeing here, if we look at it carefully, with the help of standard interpretation of quantum mechanics, we have to present it in terms of density. That is the only way I can have interpretation of the wave function. And we see that at different time, this is t equals t2, this is t equals t3, this is t equals t4. At different time, densities are changing. These are just to for our eye to have a feel how it's changing. This is x-axis. So, what we see that densities are changing, and that's the way we have to represent the quantum dynamics. This is one dimensional representation, one dimensional in terms of space, in terms of position space. That's why it's one dimensional, and this is the way we represent the quantum dynamics. On the other hand, in Bohmian mechanics, we have quantum trajectory. So, I had this initial distribution of the wave function. I have tried to present this distribution and this distribution to be the same. So, this is my t equals t1 time, and this distribution in Bohmian mechanics I do not have any wave function anymore. Initial distribution can give me different position of the particle, different possible position of the particle, and it shows at different time how these individual particles are moving with a velocity each particle will have certain, each position will have certain trajectory, and these are called quantum trajectories. This is called quantum trajectory. So in Bohmian mechanics, we can directly get certain kind of trajectory equivalent to classical mechanics, but the only difference is that, remember, we have only one particle, and this many trajectory. What does it mean? It means that if the particle was at this point, there was a possibility, because this is the distribution function. Distribution function is showing how possible positions are applicable to that particle. The particle exactly where it is, I don't know, but there are possible positions, and if I pick up one of the possible position, what kind of velocity it will have, that will be given by the Bohmian velocity, which is nothing but the space derivative of the phase function, where we have assumed that the wave function had following form. One can argue that instead of taking this kind of form, what about if I take this kind of form? Axt is fine, but e to the power minus I h cut s xt, that's also fine. Probably will end up with some other interesting information. So any kind of form one can use. We have used this form because this conveniently leads to certain useful information, and if I use this kind of form, then I get the velocity of individual velocity of the particle for individual possible position, initial position. So if I start with this x naught initial position, its velocity as well as the trajectory will be different than x1 position, then x3 position, x5 position, x6 position. All these different positions of initial positions will be giving me different trajectory. So that's the difference between Bohmian mechanics and standard interpretation of quantum mechanics. In standard interpretation of quantum mechanics, we'll always deal with the wave function, and because wave function cannot be observed directly, we have to convert it to density, and we'll see how density is changing as a function of time. That is the manifestation of quantum dynamics in standard interpretation. In Bohmian mechanics, on the other hand, we pick up the possible position, initial position, and then each position will be now giving me individual trajectory, and finally all this trajectory collectively shows how they are behaving. So this is the primary difference between the standard interpretation of quantum mechanics and Bohmian mechanics. We'll move forward and we'll look at the real part. Now real part would be, this part would be real. Now this part is real, and this part is real, and this part is real. And remember, we have removed this exponential term because we can take it out. So the real part, if I write down the real part, is going to be minus a time derivative of the s function equals minus h cut square by 2m space derivative of a function plus a by 2m whole square plus VA. That's my real part. I will reorganize it plus 1 by 2m whole square plus v equals h cut square by 2m a second derivative of a with respect to x. And we will write down this equation as follows. This term will assume to be a q term. What does it mean by q term? We'll assume to be minus q term, minus q. So this is nothing but minus q. There is a particular meaning of this q term we'll get to know very soon. And we understand that this q term, which is nothing but h cut square by 2ma x2, it is a function of x, t and rho. Why? Because a is a function of xt, that's why it is function of xt, and I have this a term. A is nothing but square root of rho. So that's why q term, I have introduced this q function. This q function is a function of xt and its density. I will rearrange this equation. Minus v plus q. Now we will take the position derivative of this entire part. If we take that, plus 1 by 2m is going to be minus position derivative of v plus q. V is the potential term, we remember that. So from here we get this partial derivative plus 1 by m. This is going to be ds. This is 1 by 2m, and this is going to be 2 this, and then is nothing but minus v plus q. So this 2 will be gone, and I get back this equation. And we have already understood that this ds dx equals mv. That's the velocity we get, local velocity or Bohmian velocity. This is called local momentum. Why it is local momentum? Because this is a momentum represented by the particle for each individual initial position coming from the initial distribution. So if we do that, local momentum, and we can take the second derivative, and that's going to be m dx. So we have to use this because this is a term which we have here. So we're going to use this one here, and as a result, another thing which we have to do here is this one can write to be equal if both mixed second order partial derivative are continuous around every point on the x-axis. So as long as S is continuous function, we'll be able to write down this one. So if we write down this one, then what we have is this is nothing but time derivative of, and we know that this is related to momentum, so this is going to be mv, which is time derivative of this. So we have now this term evaluated. We have already evaluated this term, so we can plug that in. This two, if we plug that in, we get back a simple equation like this. Minus v plus q. So this part is velocity v, this part is given here, and this part is given here. Now, because velocity is a function of both space and time. Why? I have showed already so if this is the initial distribution function, then these are the possible positions I have for the particle. Anywhere it can stay, but at the same time I have to mention here that although there is a possibility of the particle staying anywhere in this, but there is a mean position also that is given by expectation value. So those are the standard interpretation of quantum mechanics. Here we have these possible positions, and each position will be now undergoing some motion and this motion is represented by the quantum trajectory. So, this velocity in the end depends on its position, from where it's starting. If it is starting from here, then it will end up with going somewhere else. If it is starting from here, it will go somewhere else. So, it depends on velocity, depends on both space and time. Velocity has to depend on time also. So, because it depends on both space and time, this total derivative, which is not partial derivative, total derivative will be given by partial derivative summation of these two partial derivative. And that's exactly what we have here. And this dx can be represented as v dt. That's the displacement you will have, or by this mathematical trick what I get is the total derivative, the total time derivative of the velocity I get, and that can be represented by summation of these two partial derivatives, v dv dx, and that's exactly what we have here. So, this equation can be simplified as follows. Is going to be m total derivative with respect to time equals minus v plus q. This equation we get. So, what it suggests, if it was a classical particle moving under conservative force, then we write that force, which is nothing but m dv dt, is minus gradient of the potential. That's the way you write. So, this is the classical force equation. And in Bohmian mechanics, what we get is this equation, which is very comparable, very close to the classical equation, except for the fact that I have now additional term which is q. So, it is not just the potential, there is another potential which is introduced, and this part is called quantum force, dq dx. This part is called quantum force. So, what it points out that an important information here is that if a state of a moving quantum particle is represented by psi xt equals a xt e to the power I by h cut s xt trial wave function, where a and s are both we are considering real, then A gives me probability density of the particle at a given time. So, this is related to the probability density. On the other hand, S function, this gives me the local velocity or Bohmian velocity, which is given by the space derivative, and that's why Bohmian mechanics gives me quantum trajectory. So we have pretty much come to the end of the presentation, this module. We have made an attempt to understand quantum dynamics with classical mechanical flavor, with classical mechanical idea. And the only difference between classical mechanics and quantum mechanics is that in classical mechanics we can draw a trajectory. And trajectory, what does it mean? It means that in xt plot, I can find out the particle position, exact position at different time. In quantum mechanics, I cannot get that information directly because the particle will be represented by a wave function, and wave function itself is a delocalized function. So what can I do? How can I get that classical idea in the quantum dynamics? There are three theorems I have presented. Ehrenfest theorem, where I have seen that expectation value is following classical mechanics. What is the definition of expectation value? That I have already presented. Hydrodynamic formulation, second theorem, where we have shown that this quantum dynamics can be represented as a flow of density, and flow of density solely depends on the current, probability current at that point. So if these 2 points if we consider and this space we consider, and if the inner current and outer current are different, then there will be a accumulation or decay of the probability at this region. So this is called hydrodynamic formulation with the help of probability current. And the third formulation we have shown is Bohmian mechanics, where we are assuming that the wave function, which is supposed to present the superposition state, but I am intelligently selected a particular trial function for that kind of evolving system, time evolving system, and then plug that in, and I am getting a local velocity. And in addition to that, I have some additional information which is related to the quantum force as well. What is the meaning of quantum force? Those are the topics which will not cover in this course, and we will not much discuss about the Bohmian mechanics, except for the fact that we will be presenting translational motion, free particle motion, the behavior of a free particle motion with the help of Bohmian mechanics. That's the only topic which we'll cover in this course. But it's an open topic, and there are many terminology which are used very frequently, hidden variables. Those things will not present here. So we will end this module. I will see you again for the next module.